voltage. In Ohm's law and in Watt's law, it's symbolized by V, or an E, I prefer V. The units for voltage are volts. And the 1 volt is equal to 1 joule per coulomb. So that's a measure of energy per a measure of charge. So volts are the energy per charge. And if we want to solve for it, V is equal to I times R. Cool. Also, the voltage is analogous to electrical pressure, or how much these electrons are being scrunched together, how much they want to move. So right here I've drawn a whole bunch of electrons denoted by a little circle with a little minus charge in them, and they're all being smushed together. Now electrons don't like being smushed together. They want to move and expand and reach an equilibrium through whatever conductors they're connected to. So if we have all of these scrunched together and there's a conductive path, we're going to get a current. A current, symbolized by I, is measured in amps, or amperes. And an ampere is 1 coulomb per second. So you can see that it's a flow rate. It's an amount of charge moving past a point in the circuit per second, or per time. If you want to solve for current, I is equal to the voltage divided by the resistance. And we can equate this to flow within water systems or other things like that. So you see we have electrons, and they are flowing in a direction. Now the flow isn't always just in a straight line. Because these electrons are flowing through conductors, they're going to be bumping into atoms and changing direction as they move through. And that collision, or those collisions through the conductive medium that they're going through, is what gives rise to resistance. Resistance, denoted by R, and measured in ohms, symbolized with an omega, is equal to a joule second per coulomb squared. Just remember that it's a measure of resistance. So to find R in Ohm's law, R is equal to V divided by I. And it's the resistance within a flowing system. So just like was said earlier, as the electrons are flowing, they're going to be bouncing off of all of these atoms in whatever conductor they're in. So you have an electron coming in, boom, 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 and out the other side. Now all of that resistance, all of those collisions at the atomic level are going to dissipate energy. Because we know that the current is conserved, if you have the same flow coming out of the battery, you're going to find that same flow coming into the resistor, coming out of the resistor, and going back into the battery. That is, the circuit keeps the same current. So the resistance is not decreasing the current within the circuit, but it does have to dissipate electrical power. We'll get to that in a moment. So that electrical power is dissipated by the voltage. As electrons flow through a resistor, the voltage drops. And we'll talk about how that's given off as power. Power, symbolized by P in Watt's law, and measured in watts, capital W, is equal to a joule per second. So a joule is a measure of energy, and a second is a measure of time. So this is energy per time. So when we want to solve for power, given Watt's law, its power is equal to I times V in simple form. You can also use substitution with any of those symbols over there if you wanted to get rid of the V in this case. You just use V is equal to I times R, and you have P is equal to I times R, or I squared times R. So algebraically, these are very manipulable, which is good. Manipulatable, which is good. So the energy consumed per time is what we know as the power. If you look at a 60-watt light bulb, it consumes 60 watts of power. So in the filament, which is a resistive element, there are lots of random collisions as the electrons flow through the filament. All those collisions give off energy in the form of photons, visible light photons that we can see, and also infrared photons that we can't see but we can detect as heat. So that is the power given off by the electrical flow. As the current flows through, power is dissipated, which means that the voltage drops through the resistor. So what I'm going to do is have you guys ask a couple of questions. So these are questions from the audience here. All right, go for it.
What's Ohm's law?
Ohm's law allows us to find the current, the voltage, or the resistance within a circuit.
Explain what's on the board, please.
All right, I'll re-explain it, just briefly though. What I've got here are 4 symbols. We have V, I, R, and P. These are symbols for voltage, current, resistance, and power. These are elements of Ohm's law and Watt's law. Ohm's law is V is equal to I times R. So that's our basic, how do we get circuits and solve them. The current, the voltage, and the resistance are all related by Ohm's law. Watt's law over here, power is equal to current times the voltage, is going to allow us to solve for the power within circuits, or realistically the power lost through loads. Loads being resistors, motors, things like that. So this is how I'm going to visualize it all. The voltage is like the electrical pressure. So if you pack a bunch of electrons all tight together, they're going to want to move. They want to be evenly spread out. It's kind of like if you had a whole stack of marbles on the floor. They don't want to be in that stack, in that big old mass of marbles. They want to spread out to even. So they will all move, flow, to get to a nice uniform equilibrium state for them. Electrons will do that too. They'll spread out through the circuit, and as they move, that causes the current. But the current bumps into a whole bunch of atoms as it's flowing through conductors, and all of those atoms, all of those collisions cause resistance. Now that resistance doesn't decrease the current stays the same, but the resistance does decrease the voltage. So as the electrons are flowing through all of these conductors with all these atoms and bumping into them, they're giving off some energy, some power. So energy consumed per time by the resistor, like in a light bulb. In the filament of the light bulb, you see it incandesce, it glows. And that's because all of that electrical energy, or some of it at least, is being converted into light and heat by the resistance of the filament. And as it does that, it dissipates power. The resistor of the filament dissipates power, and it also dissipates the voltage.
Can you explain how some of those units fit into Ohm's law and Watt's law?
Okay, cool, good question. So, a volt is a joule per coulomb. So a coulomb is a unit of charge. A joule is a unit of energy. So a volt is a unit that describes charge or energy per charge. So if you have a certain amount of energy per the charges that you have, that's your voltage that you've got. Amperes are coulombs per second, so that's a flow rate. It's an amount of stuff flowing past a point in the circuit every second. Ohms, this is a little bit confusing, so I won't go fully into it, but it's a joule times a second over a coulomb squared. Mathematically, this works out because an ohm, or the resistance, is equal to the voltage divided by the current. So voltage is joules over coulombs, and the current is coulombs per second. When you divide joules per coulomb over coulombs per second, you get joule seconds over coulomb squareds, which is that. But don't worry about that unit all too much, because it's hard to reconcile. A watt is a joule per second, so it's the amount of energy consumed per second. So the joule is energy, second time. That's pretty self-explanatory there. And then you can see how Watt's law for determining the power is equal to the current times the voltage. Well, if we have the current, coulombs per second, and the voltage, which is joules per coulomb, coulombs will cancel out with each other as you multiply them out, so you just get joules per second.
The power source come into a standard electrical system?
Okay, so when you have a power source, are you talking like a DC power source in a circuit? All right.
Yeah.
That power source is going to output a certain amount of power. So that's a certain amount of voltage with a certain amount of current, because the power is given by the current and the voltage. So if you have, let's say, a power supply, like one of these. Power supply. That's going to
Which is very low.
feed into a circuit, and that will provide the voltage necessary to push the electrons in its current and the electrical current around through the different resistors of the circuit, or the different loads in the circuit, because the resistors, or all loads, have that resistance there. If the current is flowing through something, unless it's a superconductor, it has resistance.
What's a superconductor?
Ah, good question.
That's a great question.
A superconductor is a material that has almost no resistance. So see how the electrons, as they're flowing through, typical materials are going to bump into the atoms around, and they're going to give off energy in the forms of heat, light, other forms of energy that are given off. Like if you have electric motors, you're turning electrical energy into mechanical energy. A superconductor doesn't have this problem. The atoms can flow through, or the electrons can flow through a superconductor with little to no resistance at all. Usually this is a result of the temperature, because as materials cool down, temperature is a measure of the average kinetic energy of a molecule, or of the molecules within a substance. So if you cool down the molecules within a conductor to very, very, very cold, then what's going to happen are all those molecules stop vibrating so much. They lose their kinetic energy. And when they are more stationary, the electrons can flow through them without as many random collisions as they do when they are warmer. So those would be certain classes of superconductors that rely on temperature. There are more high temperature superconductors, so you don't have to cool down so much, and they're made with exotic combinations of alloys, and they're very cool. That's a very cool industry that people are starting to exploit nowadays. Yeah,
How do you know all this?
you read a lot.
Oh, that's it?
Reading is good, and I don't know everything, but what I do know, it comes from just reading things, lots of things. Yeah.
What are electrons made of?
Electrons are tricky to say exactly what they are, because we have different models of the atoms, and electrons were discovered through a whole progression of things with Rutherford's experiments, and then that discovered the nucleus of the atoms, I think, when he was shooting protons at gold foil. But then electrons, we've modeled them as finite particles before because we can release them in individual chunks, as individual molecules. But the more we go on with science, the more we're finding that electrons are just a perturbation in the electromagnetic field. So the electromagnetic field is in everything, and electrons they exist as a probability region within the electromagnetic field. So they are likely to be in places. It's likely that you'll find them in certain orbits around atoms, but it's not necessarily the case that they'll be there. They could be on the other side of the universe, but it's a very, very vanishingly small chance.
What's the difference between watts and ohms?
Watts are a unit of power, so they measure the amount of energy that's utilized by something every second. Ohms are a measure of electrical resistance, so they measure how difficult it is for the voltage to push a current through something. They effectively give us how much voltage is going to be lost by a certain current moving through a certain material.